alternating series. So thus far we have dealt with series with only positive terms. An alternating series is one whose terms are alternately positive and negative. So you've got here 1, then negative a half, then positive a quarter, then negative an eighth, then positive 16. So it's alternating, obviously, between positive and negative. Now, the alternating series test. If the alternating series test for a series from 1 to infinity of negative 1 to the n minus 1 times bn. Now notice, girls, bn is outside the negative part. So bn is actually always positive. Okay? It's the negative 1 is separate to the bn. Okay? Does that make sense? So it equals b1 minus b2 plus b3 minus b4 plus b5 and so forth. So it satisfies this inequality. 0 is less than or equal to bn plus 1 is less than or equal to bn. In other words, each term, the size of each term is smaller than the one before it. Does that make sense? So look at this one up here again, for example. The size of a half is smaller than 1. The size of a quarter is smaller than a half. The size of an eighth is smaller than a quarter. Do you know what I mean? So the size of each term is decreasing, and also the sign is alternating. So we say if the series satisfies this inequality, so in other words, again, the terms are decreasing, like the size of them, and the limit of bn equals 0, then we can say the series is convergent. This is just another way they sometimes write this inequality. Okay, these actually mean the same thing. The theorem also applies if the first term is negative, since we can multiply through by negative 1 and proceed as above. So like you can take the negative out and then have a positive b1 and a negative b2 and a positive b3 and so forth. Does that make sense? And then as long as if the inner series converges, then the whole thing converges. Doesn't matter. Now, I want to explain why it converges. The convergence process is illustrated in the following diagram. So just look at this. Basically, the idea is if b1, for instance, is positive, and it can work if b1 is negative, we just take the negative out. But if b1 is positive, and then we minus b2, because b2 is smaller, we won't go all the way back to 0 or past 0. We'll just go back part of the way. Do you get what I'm saying? Like in size. Is everyone okay? Like if it was on a number line. Then when I add b3, that is smaller than b2, so it's smaller than the amount we went back by already. Therefore, we'll add a smaller amount, so we end up somewhere in there. You getting it? So that's why we're there now. Then if we minus b4, we add an even smaller amount and end up in here. Then we go like that and so forth. And we just keep getting smaller and smaller until we're somewhere in the middle there. And that's the point in between there that we're converging to. And so that's why we're converging the sum, because we're adding and subtracting them, is converging to somewhere inside, in between 0 and the first b1 term. So question 1. Show that 1 minus a half plus a third minus a quarter, blah, 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 which equals that is converges. So girls, again, we need to show that bn plus 1 is smaller than bn. So we need to show this part, and we need to show that the limit of a term is 0. All right, so first of all, what is bn? Just bn. Yes, good. Now let me explain that again. Girls, this sum can be written as the sum from 1 to infinity of negative 1 to the n minus 1 times 1 on n. So that there is bn. So what's bn plus 1? 1 on n plus 1. So tell me, is Bn plus 1 smaller or equal to Bn? It's smaller, yeah, so it's true. And it's bigger or equal to 0 because n is bigger or equal to 0, bigger than 0, I should say. So therefore, Bn plus 1 is smaller or equal to Bn. What else do I need to show it converges? The limit. So now the limit as n approaches infinity of Bn equals the limit as n approaches infinity of just 1 on n. What does that approach? As n becomes infinity, that whole fraction becomes just 0. That's it. So therefore, we've shown both properties that it has to hold to be convergent. So therefore, the series n equals 1 to infinity, negative 1 to the n minus 1 over n converges. And that's it. But, I mean, let's get into the habit and assume we have to. It'll increase your chances of doing it right in the test. Suppose a convergent infinite series converges to a sum of S. The nth partial sum is used to estimate the sum S. Remember, like last lesson, we estimate a sum by going up to like k. Here we're going up to n instead of k, no big deal. And the error is now, we call it the truncation error, is defined by Rn equals the absolute value of S minus Sn, just because we're interested in the size difference, which is why we do the absolute value. Yeah, we call it truncation error. The alternating series estimation theorem. Suppose S equals n equals 1 to infinity of negative 1 to the n minus 1 Bn is the sum of a convergent alternating series, so that Bn plus 1 is less than or equal to Bn, and the limit of Bn equals 0. So they're the two properties for a convergent alternating series, as we know. The truncation error, which is S minus Sn, absolute value, is less than or equal to Bn plus 1. Let me explain that. So I'm just going to take a moment here. Okay. This is because S minus Sn, what terms are not in Sn? If you're adding up the B1, B2, B3, B4, B5, what's the next term that isn't in Sn? Bn plus 1, yes. And what's the term after that? Yes, but we would end up alternating in signs, wouldn't it? Minus Bn plus 2 then, plus, and so forth. Oops. Now remember, you know how that idea, if Bn plus 1 is here, then n0 is here. When we minus Bn plus 2, will be somewhere in between the two because it's smaller. Then when we add Bn plus 3, it'll be somewhere between them. And minus Bn plus 4, somewhere between there. Yep. So the point is it'll keep bouncing back and forth until somewhere in there, right? Now, whatever value that becomes is less than Bn plus 1, right? So therefore, this sum must be less than or equal to Bn plus 1. Does that make any sense there? Beautiful. So, find the sum of that, correct to 3 decimal places. Okay. First of all, what's Bn? What is Bn plus 1? Now, first of all, girls, what I'm doing is I need to show it's convergent so that then I can use this idea here. Is everything okay? Otherwise, I can't use it if it isn't convergent. And so tell me, is Bn plus 1 less than or equal to Bn? Yeah, this is less than or equal to Bn. 1 on n factorial, which is less than or equal to Bn. Is everything okay? And what's the other thing I need to show? The limit. As n approaches infinity of Bn, equals the limit as n approaches infinity of 1 on n factorial. Everyone cool? Which is 0. It is just 0. It's definitely going to approach infinity on the bottom, so that becomes 0. No problems there. So therefore, we know the series converges. Now that we know that, we can consider the series. Now, okay, so I want to round it correct to 3 decimal places. So in other words, what do I want my error to be less than or equal to from last lesson?
0.0005.
Yes, 3 zeros. 3 zeros, exactly. Therefore, now, I might make a note, correct to 3dp means my error, what is it, Rn, needs to be less than or equal to 0.0005. Now, what on your page do you know Rn is less than or equal to?
Bn plus
1. But Rn is less than or equal to Bn plus 1, so I must have to use that. So what I need to know is what value of n is Bn plus 1 less than or equal to 0.0005. So I might write that down. Therefore, so when is Bn plus 1 less than or equal to, or less than 0.0005? That's the question that I need to find right now. Is everyone okay? Okay, cool. Let's find all that. What? So how do we know to put Bn plus 1 less than or equal to 0.005? Basically, we know, according to the theorem, we know that Rn is going to be less than or equal to Bn plus 1. We want Rn to be less than or equal to 0.0005. So for Rn to definitely be less than 0.005, we should find a Bn that is less than it. Then Rn will also be less than it. Let's have a look at our Bn's, B1, B2, B3. What are they? Okay, so let's have a think about that. You can either just write it as B1 equals, B2 equals, and so forth, or we can write it as a series. Because I know where this is going, I'm going to write it as a series. Okay, I'll show you what I mean. So girls, hopefully you have enough room. We'll see how we go. So girls, the series, or S, is, what would the first term be? And you can see the question. When n is 1, what do you get? Just 1. 1 over 1, which is 1. And then what about when n is 2? Okay, let's keep going. What about when n is 3?
plus a 6.
Plus a 6. 3 times 2, yes. Okay, let's keep going. What about n is 4? Minus 1 on 24, yep. Okay, since we know we're alternating, we can just put plus straight away. What about B5? What about B6? You just have to times 120 by 6, which is 720.
Oh, so close.
And then finally B7 times that by 7. You can do it. 5,000. No, you were closer a second ago. 5,000 and... I'm just going to tell you 40. All right, now, and that keeps going. Now, I just want to point out this is obviously B1, B2. I might do that in red. B3, B4, B5, B6, B7, blah, blah, blah. Let's check the actual values of these as decimals so we can compare it to 0.0005. In your calculator, can you tell me what 1 over 720 is? 1 over 720.
1 point.
No, it's not 1 point.
No, 0.001.
0.89. Is that less than 0.005? Girls, is that less than 0.0005? No, that's bigger. So let's try 1 over 5,040. So what is it? 0.
0.00019.
Beautiful. Good. So in other words, B7 is less than 0.0005. So therefore, my Bn plus 1 must be B7. Does that make sense? So if my n plus 1 is 7, my n is 6. That means that the error, and what value of n do I use now? 6, the one we found. So the error after the first 6 terms is, it's s minus s6, which is less than or equal to this value here, or I might write it as a fraction. Actually, no. Let's write it as a, as a decimal. Now, girls, how do I'm trying to find s. Sorry, I'm just getting us back to sorry, I'm running out of room. But I'm just trying to get us back to everything. So at the moment, I know what my error is less than. And I know if I take the first 6 terms, I can find, I can approximate the sum to 3 significant figures. So what is this S6? What do I do to find S6? Add B1, B2, B3, B4, B5, B6. So in other words, add from here to here, just up to B6. Can you tell me what that becomes? Approximately 631944. Maybe a few decimal places difference anyway. So basically, what we're saying is the error between those two is so small that it'll be correct to 3 decimal places. So therefore, that is actually our answer to, and if we round it now to 3 decimal places, it's approximately equal to that. Now, therefore, so let's just do that. Therefore, S is approximately 0. We wanted 3 decimal places. So what's that? 632. Now, can I just show you something else now? That's really all you need to do. But to convince you a little bit more, can I just show you something? We just said S6 is approximately 0.631944. I'm now keeping the decimal places. Is everyone with me? But we also know that S minus S6 is less than or equal to that decimal we found before. Right? Now, so therefore, if I now put that in a new equation without the absolute value, S minus 0.631944 should be between the positive version of this and the negative version. Does that make sense? So to solve that for S, I would add 0.631944 to every little bit, every kind of side. Now if you add those up, on this side they cancel out. So I get S in the middle is in between. On this side I get 0.632144. And on this side, I get 0.6317456. Slightly different, but what happens when we round both of those to 3 decimal places? You get 0.632 for both of them. And so that's why it's correct to 3 decimal places. Now, I believe the idea is you should be able to stop over here when you get to this and around that, because the whole idea is the error should be so small that it won't make a difference. You'll still get that, which we showed it did. Okay? So I still think that's fine, but I'll just show you, I just wanted to show you this because to show you that it does in fact work. Okay. Absolute and conditional convergence. Given any series, sum of 1 to infinity of an, we can consider the corresponding series where we take the absolute value of each term and add them, whose terms are the absolute values of the terms of the original series. So basically, we say that the series is absolutely convergent if the series of absolute values is convergent. So we can find that out by realizing that the limit of an is 0. Is that right? We'll have a look at our notes. Clearly, if an is bigger or equal to 0, then absolute convergence is the same as convergence because the absolute value of the term is the term. But there are series, such as this one here, which is convergent but not absolutely convergent. And that's called conditionally convergent. Okay, so theorem of absolute convergence. If a series is absolutely convergent, then it is convergent. Now, basically, you can't go backwards. If a series is convergent, it doesn't mean it's absolutely convergent. So, show that cos n over n squared is convergent. What do we do when we see cos n? Squeeze theorem. So, we know that cos n on n squared is between what? 1 on n squared and negative 1 on n squared. But because we're talking about absolute convergence, let's take the absolute value of it. In other words, what about the absolute value? So the absolute value of cos n on n squared is less than or equal to what? Oops, less than or equal to 1 on n squared. But what do we know about the sum from 1 to infinity of 1 on n squared? Do you think it's convergent? Why is it convergent? Because the limit of equals 0. And, yeah, no, that's right. So therefore, this is convergent. So therefore, by the squeeze theorem, wait, one thing at a time. By the squeeze theorem, I wish I could just do that. Squeeze theorem, this is convergent, but this is absolute value. Though I think you could say it for both, but anyway. Is convergent. So therefore, by the theorem of absolute convergence, the sum of just cos n on n squared is convergent. By theorem, I often use THM as theorem. Abs, let's just do abs conv. By theorem abs conv. They know what they mean. I mean, I can't say that you'll get full marks in a test, but you know. Okay, the ratio test. Another one. But we've actually seen the ratio test before, haven't we? And now we're just using it with absolute values. So the ratio test can be used to determine whether a series is absolutely convergent and hence convergent. Because if it's absolute convergence, it is just normal convergence. So if the limit as n approaches infinity of an plus 1 over an absolute value is less than 1, it's absolute convergence. That's also because, think of it, that's kind of like that alternating theorem, the alternating series, because that means the following term is less than the previous term, for that to be less than 1. Do you get what I'm saying? If limit of n approaches infinity of an plus 1 over an is bigger than 1, then it's divergent. Well, that makes sense because our terms are increasing. Therefore, the series must be approaching infinity. If the limit as n approaches infinity of an plus 1 over an equals 1, the ratio test is inconclusive. That means the terms are equal, which I think it would eventually add up to infinity, to be honest. But I think it's not enough to say from that to say it's divergence. That's why they say it's inclusive. You've got to do more work than that. So now, test AN equals that for absolute convergence. So obviously we're going to use that ratio test ID. So girls, if that's AN, what is AN plus 1? Oops.
N plus 1 times n plus 1 cubed over 3 to the power of n.
Okay, it looks ugly, but it simplifies nicely when we put one on top of the other.
Sequences again here, or are we doing series? Are we still doing series?
Okay, so good question, good question. We are going to check the series is convergent by looking at the individual terms. So in the end, we're going to say, so the sum of blah, blah, blah is convergent. That's a good point, girls. That's a good point.
Test the sequence, test the actual.
Oh, okay. I think it's just a badly worded question. I think what it should say is test. See how it says then the series is convergent?
Yeah.
So really, what we should be doing is test that.
Okay. Sorry.
No, I agree with you. Where AN equals that for absolute convergence. That's a better worded question. You're right. You're actually right about that. That's a badly worded question. Okay. So now that we've got that, let's do this side. Let's do the limit as n approaches infinity of AN plus 1 over AN and see what that equals. And what's nice is lots of things will cancel out. So it becomes a limit as n approaches infinity. Now, because each one is a fraction, I'm going to do the one fraction divided by the other fraction rather than have fractions and fractions. So what's AN plus 1? It's all this. And I want to divide that by AN, which is that. Okay, before you go any further, what's something I can cancel out right now? Yes, we are going to get to that. We are going to get to that. But I'm going to deal with the fractions in a second. But can you see something I can cancel out? The negative ones, first of all, no matter what they become, I'm going to take the absolute value anyway. So it doesn't even matter. They don't even need to be there. So now let's just focus on the fraction bit. Okay, so it becomes okay, what do you do when you divide by a fraction? Times by its reciprocal. All right. Okay, so any thoughts? 3n and the n plus 1, so it's just 3, in other words, yes. Now, the other ones are weird. So basically, what I'm going to do now is I'm going to take 1 on 3 out. Is that okay? It's like invisible 1 on 3. And now I've just got n plus 3 cubed. Is that right? N plus, I have 1. I've changed this to a 3 at some point. Sorry, girls. This should be, this should be, do it for me. This should be 1. This should be 1. This should be 1. 1, 1, 1. Is everyone okay?
Yeah.
Over n cubed. Is everyone okay?
Yeah.
Okay, now am I allowed to do 1 on 3? Take 1 on 3 out of the whole limit?
Yes.
Yes, because it isn't involving n. Now, girls, what I can rewrite this as is, does anyone want to guess?
Oh, because they're both 2 and 3.
Yes.
3 out.
Yeah, kind of. Basically, you can make it n plus 1 over n all cubed. Have a think about that. Does that work using index laws? Good. Now that we've done that, let's just look at that inside of the brackets. I want to split that up. So it becomes n on n, which is plus 1 on n, all cubed. And now I think I'm ready to sub in n is infinity. I'll just let you catch up, and then tell me, what does that become? What does this part here become? 1, because it's like 1 plus 0 cubed. I might even write that out. 1 plus 0 cubed. So it's 1 on 3, which is less than 1. And according to the ratio test, what does that mean? It is absolute convergence. So basically, now the series of n equals 1 to infinity of an, or this, is absolutely convergent. So girls, what happened at this point? Whoops. So I've got do you see how I'm dividing by an? What happened then? How did that simplify? So that cancels out with the factorial part of that. And what happens with the other one? Yeah, that cancels out with that, so it's just k. And then what does that become? The limit. 0, which is less than 1. Therefore, by the ratio test, the series of n is 1 to infinity convergent. But that wasn't what we were asked to do. We were asked to show that k to the n of n factorial equals, the limit is 0 for the limit. Yeah, I don't think so. And we're done.